Now we want to do the CNLS fit to deconvolute the electrochemical processes. Then what we can do is we can go back to the main page with sources. We click on the CNLS fitting. Then we will have a clear view first with the DRT that we derived from the previous step. And then again, on the top left, we have the file list, and then we have the parameters window, and we have the buttons for the data processing, the displayed file, and also a window for all the tables of all the parameters. So here we want to fit, let's say, each peak of the DRT based on our knowledge. So I'm dedicated for high temperature electrolysis and fuel cell. So here I will use the most comfortable example for myself, but you can always try with your own data. That here we can, if you put your mouse on the plot, you can see a cross. So for the cross that you placed on the bottom right, you can see two numbers. So it is X and Y number for the point for the cross. So for example, if we put on the highest peak, we have 2.09 for the frequency, and we have 0.146 for the gamma, which is the ohmic times time times square centimeter. So what we need to do is first we identify how many peaks we have. For example, the small peak here, we can consider it. Let's say it's 0.31. We have 1, 2, 3, 4, 5, 6. Let's say 6 peaks. For the highest frequency peak, if we use a Tikhonov methodology, it's generally not closed if we have some inductance factor. We can fit it, but we can also ignore it, but we can try. So we have 6 peaks, and then we need to adjust the corresponding parameters to make sure that we have the correct numbers of elements to fit the peaks. So on the left-hand side, we have the list of all the elements, L1, R2, it means the first inductor. R2 means the ohmic resistance, so we always need a resistor to fit the ohmic resistance. And then on the right-hand side, we have the segment constraints. This is a button that I reserved in the future for some other functionality. I recommend you to always keep it ticked, and we will release the update log to explain in the future how we can play around this parameter. And then we have R counts and tau counts. It means the constraint of the resistance and the constraint of the time constant. I will show you how it works later. And then we have the data type. So the fitting that we are going to perform based on using the equivalent circuit model is targeting the impedance data. So now if it's truncated, it means that we are targeting the original impedance data that we measured with some noise. And if we look at the truncated RBF, if we select it, it means that we are going to fit the impedance data that is already fitted from the RBF DRT methodology. And smooth KK, it means we are going to fit the data the impedance data that is smoothed by the KK methodology. For most of the time, I recommend to keep it by default with the truncated data, because this is the most reliable. This is the reality. It does not have any artificial impact from the previous fitting. So we click on it. And the number of the peaks, it's another very convenient functionality. I will go back to that later. It's a second approach. And then the number of iterations, it means that during the fitting, how many iterations of fitting that we are going to perform. Normally 5 iterations is enough to reach the minimum of the minimum residual. So just keep it like this. The number of peaks, it's 5 peaks, but I just identified 6. So what we do is we add 1 peak. And if we scroll down, We have from high frequency to low frequency, from 1000 hertz to 0.1 hertz. So what we need to do is that we select the hertz of the peak. So as you can see here is about 1.85. Let's start from the lowest frequency peak. So here we have 0.3. What we do is we put 0.3. Note that this value does not need to be accurate because it is just used to determine the upper bound and lower bound, the constraint during the fitting for the equivalent circuit model. And then the second peak, which is 2.31. This peak put across here is 43. And this peak we have 330-ish. This peak we have 1,800, and this peak we have around 1,005 or 15,000. Okay. Now we have 6 peaks. Then what we need to do is the fact that we need to add 6 elements. So you can add RQ element. So here I only give RQ elements as an example, but you can play with it later. What you can do is to add RQ elements one by one, or what you do is just you open the selector. You can see the elements that can be added for option. The already selected, already added elements are L1, R2, RQ3, RQ4. Custom topology, I will go back to that in the end because it's an advanced methodology that is generally seldom used. What you can do is click here, RQ, 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 RQ. Now we have 6 RQ elements. Okay, that's the corresponding number of the peaks. So what we do is that we say confirm. Then we will add 6 RQ elements, numbering from RQ3 to RQ8, from the high frequency to low frequency. RQ3 corresponds to 15,000. RQ4 corresponds to 18,000. Now, what we do is we initialize a parameter. And you can see the value table here is completely changed. So for the parameter table here, the first column is a name. The second column is a type. You can change the type to RC or RQ if you feel like RQ is not comfortable for this peak fitting, whatever you like. The third column is a parameter. We have R for resistance, tau for time constant, alpha for the dispersion factor. We have the value, which is initial guess, because fitting is a way of optimization to minimize the model and the difference between the model outputs and the reality. So we need an initial guess to make sure that we perform we can start from a good point so that we can have the most reliable fitting. And the upper bound, which is how far this parameter can go. For example, if it's INF, it means infinite. It can be like infinite, the number, but normally to have a good fitting, it won't go there. LB, it means the lower bound. What is the lowest value it can go? So by default, it's a 10 to the power of minus 10. And yeah, and then take RQ3 as an example. For the resistance, we do not put a constraint now, so it is free as a bird. It can fly whatever it wants for the resistance. And for the tau for the RQ3, the time constant, it has to be maintained within this range. I will explain you how these are determined. And then for alpha, it's always determined between 1 and 0.4 to determine the dispersion, dispersion, the non-ideal extent of this, how non-ideal this electrochemical process it is. So now let me explain you how this time constant is performed. Let's make a simple draft. So what we did with frequency determination, for example, let's consider 0.3 and 2.3 and 43 hertz. We determined we determined a peak here, a peak here. Wait a second, maybe I'm not sharing it. Let me check the display. Okay. Okay. Yes. Okay. Now it should be shared. Yeah, that's good. Let me give you a quick explanation how the time constant upper bound and lower bound is determined. So we put 0.3 for this one and like a 2.3 for this one and 43 hertz for this one. And we want these RQ elements fitting. Okay, someone open the mic.
So in terms of
So what we did is that to determine the so it corresponds to RQ6, RQ8 for the lowest frequency, RQ7 for this one, and RQ6 for this one. So the way we determined it is we take the log. We take the log of these 2 points. We put the boundary in between. We use this frequency range to tell that, okay, when the RQ7 in the between, which is fitting this peak, it should not move across this boundary to fit this peak. That's why we said, okay, the upper bound and lower bound is super important, and it makes sure that we will not have the RQ elements fitting the wrong processes. Okay, so that's how the boundary of the time constant, which corresponds to the frequency, is determined. And then we initialize the parameter. We can load the parameters. We do the CNLS fit. It will do 5 iterations for each data, and so it's 20 in total for 4 files. So here you can have the final fitted data here with final value, the upper bound, the lower bound, the variance, the standard error, the p-value, the probability value to indicate if this fitting is convincing or not. You have the DRT of the fitted data. You have the impedance of the fitted, of the impedance data of each element. Okay. And then if you look at the final fitting result, first of all, you can go to the residual tab here. That we have the residual fitting based the residual of the fitting. You can see how the equivalent circuit model, the impedance behaves corresponding to the measured data. Let's put the legend to the right-hand side. You can see the fitting, the curve matches the measured data quite well. So we can say it's a confidence fitting. It's a confident fitting. And then we also have the fit tab to show you how it was fitted based on the Bott plot, the Nyquist plot, and the DRT curves. So you can see that the fitted data have a quite big, quite okay, quite fine peak matching. And you can also have the elements that you can see what is, for example, if we do adjust the magnitude a bit, we can see the blue point is the measured data. L1 is for the inductance. Sometimes it's too small to be shown. R2, it is just a point, so it's generally not shown here. And you can see how the RQ3 curve from the high frequency fitting all the way to the low frequency. And you can also have the idea about how it was fitted based on the imaginary part, the Bott plot. And you can also see how each peak is fitted with each element. For example, if we put the legend on the right-hand side, we hide everything for now. And the measured data is like this. We have RQ3 fitting the highest part. We have the RQ4 fitting the frequency here. We have the RQ5 fitting here. We have the RQ6 fitting here. We have the RQ7 fitting the highest peak. And we have the RQ8 fitting a bit the lowest peak. So do not chase for a perfect 100% matching between the CNS fitted DRT and the DRT from the measured data. Both methodology, they are artificial method to treat the data. From the real impedance data to the DRT, it's already an artificial process which will introduce some uncertainty. If we do it again, with the CNS fitting itself is also an artificial process. It will introduce more uncertainty. You can never have 100% matching between two artificial processes unless you have the perfect measurement, which is definitely not there in real life. Okay, and then if you click on the all plot, you can see the trend of each file from 01, 02, 03, 04 to R2, to RQ3, to RQ4, RQ5, RQ6, RQ7, RQ8, and also the time constant and alpha, how they evolve with between different methods. So again, all the treatment here is in batch analysis. It will only be performed with selected data. If you untick on the EIS04, then when you do the treatment again, it won't process the data from the EIS04. And then we can introduce another, let's say, fancy functionality I created. So what we do, for example, we can see that the ohmic resistance, it has good trend. The RQ3, which is the highest frequency electrochemical process, we should expect, based on the trend here, we should expect that EIS02 should be located with the resistance around 0.4 instead of around 0.02. So what we can do is we unselect 01, 03, and 04. We change the lower bound because we want it to be slightly higher. We change the lower bound of RQ3 from 0.02 to 0.04. Now you can see the upper bound of this value is infinite. The initial guess is 0.02. The lower bound is 0.03. And then we load the parameter. We do the CNS fit. And this will be applied only to the EIS02 because we unticked the 03 and 04. And now if we resume, we tick them back, you can see that, okay, it's constrained to 0.04. So that you will have a good trend. But of course, this is not a scam. And we have to make sure that this won't be a scam. We have to choose and adjust the location of each point, of each measurement, of each fitting based on our knowledge. Because we know that it should have a consistent trend instead of flying everywhere. So that's how we can derive a good fitting. And of course, we can also do the same thing. For example, if you want to change the RQ3 resistance of let's say the EIS01 data, we just untick 02, 03, and 04. We can see that now we are already viewing 01, and we have the upper bound of the RQ3. The initial value is 0.05, and the upper bound is infinite, and we want it to be 0.045. What we can do is just we put 0.045, we load the parameter, we do the CNS fit, we select them all. Then you can see the ES01, the value is constrained to 0.045. So this is the way how we can adjust the fitting to make that sure that our fitting is confident. Another example is maybe the impedance of the ohmic resistance of ES01 is too low. What we can do is we put 0.0, let's say, if you look at the value, we can put 0.92. And once we change the lower bound, we change the lower bound of all the fires here. But I still keep all the fires ticked because we can see that the final value of ES02, 03, and 04, they are all above 0.092, so we don't care. Then we load the parameter, we do the CNLS fit, and you can see in the window, now it's treating all the fires 5 times again. And you can see this one is leveled up to 0.092, which is displayed on the bottom right. Okay, that's the basic idea of the CNLS fit. You can this is the basic idea of the let's say the CNLS fit. You can play with it yourself, like in the future. So now let's do one step more to see how we can have some interesting functionality. So for the first thing is the peaks. We can click on the selector from, it's not displayed like completely, but we can click on the button on the right hand side of the peaks. We can say here. Then we can manually, without inputting the frequency data one by one, we can manually select the peaks points. Six peaks, frequency, tau, gamma, everything is here. We apply the selection, and the corresponding values here, it will be changed. So this is a more convenient way for us to determine the featured frequency of each peaks. And yeah, sorry. By the way, I forgot to mention that we can remove also the elements. We can remove, for example, RQ3 if you want. Then we will have only 5 elements. We can also again add it back, but it will always add it in the button. Then you need to initialize the parameter again. Again and again, always make sure that we have the same number between the RQ elements and the number of the frequency, the number of peaks that we determined. Okay. Here we have some other interesting functionality. For example, if you open the selector, if you want to use the functionality to make a customized equivalent circuit model, what you can do is you change the equation. Now everything is connected in series, but sometimes we may have like something connected in parallel. What we can do is we change the equation here. We put a bracket. We put another bracket. It's like a math equation. Then as you can see, in the configuration of the equivalent circuit model, you will have RQ7 and RQ8 connected in parallel. And we can also add even more. For example, we can change the equation into the way that RQ6 and RQ7, they're connected in series, but in parallel with RQ8, with the whole thing in series with other elements. So, and then the fitting will be performed using this equivalent circuit model. So that's one functionality you may use in the future, but if you want to use it, you have to determine all the initial guess on your own. So it's already a non-standardized equivalent circuit model, so we need to you will need to spend some time to familiar with the option. Maybe restart the software for a lot of times to to avoid some certain bugs. But yes, it is possible. Okay, so now what we need to do is the fact that we need to resume the equation so that we won't make a mess. So we confirm. Okay, now it's good. Okay, so another small functionality I would like to introduce you about the CNLS fit is the fact that sometimes we want to tune a bit the resistances. For example, let's say this ES02 here is a bit too, let's do the CNLS fit again first. Just to refresh the figures. Let's say we find it a bit too high, but we want to still maintain to have a comparison of all the points here, because if we unselect it, we only have 1 point in the end. So what we can do is we click on the parameters. We have some options. You can click on the fix all plots. And then when you unclick the rest of the files in the file list, you will find that, okay, in the all plot, everything is still preserved here. Let's say now if we lower down the ohmic resistance of ES02 to 0.094, and then we load the parameter, the upper bound. So theoretically, it will be fitted closely to the upper bound. So you can see that the value is changed to 0.094 and it's displayed. So this functionality is to for you to have a clear comparison when tuning individually the resistances and the time constant. And then here we have some other functionalities, including X tau. If you click on it, the x-axis of the DRT and also for the rest of the plot, it will be changed from frequency to time constant. And if you put RC initialization, we will have the each peak fitted first with RC to have a good initial guess of the time constant and the resistance, because all the upper bound, the lower bound, and the initial guess based on the DRT peaks, without click on this one, is based on the Gaussian peak recognition. It's a pure mathematic methodology. But if you click on this, then it's going to use a model to fit each peak to give you a better estimation of the initial guess. But according to my experience, most of the time, they're okay. It won't make a big difference. And if you click on RSLBKK and RSLBDRT, this one is interesting because if you go back to the EIS and if you select them all, if you look at here, sometimes the fitting will give you a extremely low ohmic resistance, meaning that the ohmic resistance can sometimes be covered by the highest frequency. The highest frequency element here is RQ3. So I offer these two options to automatically set up the lower bound of the ohmic resistance based on the fitting from the DRT or from the KK. But as I said, DRT is more reliable. So what I generally do is I click on this, and when we initialize the parameter, you can see the lower bound of the R2, which is ohmic resistance, has been determined to 0.092. So this will improve the fitting quality. Okay, and then let's remove all of this to the basic functionality. So the last point is about the R constraint and tau constraint. So if we put 10, so here we have a value 10% and 100%. As I said, as I explained before, how the time constant upper bound and lower bound is determined based on the neighbor peaks, the frequency, featured frequency of neighbor peaks. So you can see the red line is the upper bound and lower bound for the fitting. of this peak, which corresponds to the RQ7. However, sometimes we want to even narrow it down more. So what we do is we set up a constraint of the time constant based on a percentage value in log scale, of course. And also we can set up a constraint for the resistance with 10%. If we click on this, we initialize a parameter. You can see we have upper bound and lower bound for all the resistances and all the time constant. You can see the upper bound has been determined to 0.101, which is 0.092 times 1.1, which is 10% margin, which is the same case for the lower bound, and it's the same for the resistance of each element and the time constant. But of course, you can change all the way to 80%, to 100%. Then you can have a bigger room for it, how it can move. But unless you need it, or you have a clear mind about what you need, what you want, it's not. You can just ignore these two options. Yeah. Okay. Now let's say we do the last fitting to refresh everything. We save the CNLS fit results. What we will derive is another folder called CNLS, and all the parameters, they are stored here. We will issue a detailed explanation about all the values, all the columns, with each Excel file generated by this software, like later on. Yes. So here we have the elements table. What is the parameter value for resistance, for time constant, for the dispersion factor? What is impedance that is fitted? So here we have the measured impedance, the mass, real part, imaginary part, the total evaluated impedance based on the equivalent circuit model, the fitted one. It's called Z total real and Z total imaginary, and Z total 0 RE, it means initial guess. The initial guess of the equivalent circuit model, but you can plot it for comparison, but normally you don't need it. The residual based on the real part, the residual based on the imaginary part, and this is impedance of each element. So normally we just add it up, then you can have the Z total. So R3, R2, RQ3, all the way to RQ8, you add it up, then you have the Z total for the real part and the imaginary part. Okay, so this is the data format. I don't save it. Yeah, sorry, of course, I forget. We also have a last sheet, which is called DRT, that you can plot the individual DRT peak fitting based on this table. We have the frequency in hertz, which is obvious. We have the DRT MES, which is a measured DRT, the DRT based on the measured data, the DRT based on the equivalent circuit model, and this is the DRT for the DRT deconvolution of the individual elements in the equivalent circuit for L1, ohmic resistance, RQ3, RQ4, etc. So all the data that you can find here, you can regenerate all the plots that is shown in the software, but you can customize it, make it nicer to adapt to different literatures. Okay, this is all for the data treatment and the process. Now, what I want to show you is what if the computer crashed, and what if you want to revisit the previous treated data? What you need to do is you close the software, you rerun it. Again, I run it with VS Code, but you can always just rerun the software by double-clicking the EISAP.py. Okay, and then what will happen is that the data will, what you have treated, the software will read all the saved data. So please do not move the CNS feed data folder, DRT folder, and ES folder generated by the software. because this will affect the data import when you want to revisit what you treated before. So again, if you click on EIS, and then you can have everything easily resumed, and sentence fitting. Everything you can have it here, and everything is exactly what you can get from the table, from the Excel file we generated.